Hey guys, it's Horner and I just want to take you through the AP Physics 1 Dynamics pretest free response questions. I think the big thing that we want to look at here is just making sure that you are ready for the test. And to get ready for that test, you've got to be able to do several things. One of the things you need to be able to do is you have to be able to complete a problem that deals with some sort of Atwood's machine. So this Atwood's machine is just a little bit different than the Atwood's machine that we did before. This one is called a modified Atwood's machine or horizontal Atwood's machine because you'll notice that this part is horizontal. We still have our vertical part, but this one is horizontal for sure. Be really careful when you do this one because you'll see there's two blocks. There's a block of mass M2 and that one is 3.5 kilograms. This one is the 3.5 kilograms. This one is M1 and it is 6 kilograms. So be really careful when you go through and read this that you don't get these confused or mixed up. You'll see 3.5 twice, that both of these stand for that M2. It does say that there is friction because it talks about the coefficient of kinetic friction, so we know that there's got to be friction there. They want us to draw a free body diagram for both objects. And the first thing I'm going to do is think about the direction of motion. And when I think about the direction of motion, you're going to notice that right here, I've said that the direction of motion is to the right, and that is positive x. Why is it then that this is also positive x? Well, it's because a pulley, which is this guy right here, it will allow you to change direction, but that's not really what it sounds. It sounds one way, but it actually means something a little bit different. By changing direction, that means that this x direction, I can make that x direction also point in the y direction. So in essence, I could also think about taking this line right here, okay, that's attached to the M2 block, and I could think about just extending it over and thinking about that M2 block being over on this side. And this is more like the train. So this is a train, and this is the engine of the train. And then over here, this is the caboose. It's on the very end of the train. So the train is pulling the caboose to the right. That's why we can do all these things with the directions. Here it is x. This is also in the x direction. So if you think about it with the train, these are both going in the positive x direction. This is no different when you have it on an Atwood's machine. It's just that this little guy right here allows us to extend instead of going to the right. It's kind of like we ran out of room on the paper, so we had to make it come down. It's not really turning or anything. It's just that the force continues in one straight line all the way across. So hopefully that helps you a little bit, kind of see what's going on. I am going to get rid of this. You don't want to draw it that way because then you will have some issues later on. Let's go back to what we were kind of talking about here. I'm going to make my pen just a little bit bigger, make it easier to see. We need to draw several of these forces, and the first force we always draw, remember, is straight down, and that one is M1G. The reason I put the 1 there is because this is mass M1. So on your paper you'll see it, but for this one I had to kind of put the dot there so you don't see it anymore. Here you do see the 2. This one is M2G, and it goes straight down. So I'm going to reiterate that 2 right there. We have pointing straight up for this one, the normal force. You could put a 1 there just so that you see it's coming from this one. There is no normal force on this block. And why is that? Well, it's because there's not a solid surface that it is attached to. Instead, this one is attached to a string, so we know that this is the tension force. For our other object, we already have the M1G and the Fn1. We know that there is tension pointing to the right, so that would be Ft. And to the left, we have the force of friction. We know it's moving to the right. The force of friction for this one is in the opposite direction of motion, and so we're just going to put Ff. It's also kinetic, so make sure you understand that this is a kinetic friction. And remember, kinetic means moving, but in our little physics world here, it is sliding. Static friction is when it's not moving at all. So kinetic friction, it's moving, but we really want to see that it's sliding. So that's really important. Let's go ahead and take a look at the next part. It wants us to derive an equation and then solve for the normal force of block M1. So remember, this is block M1, and they want us to find out what is this normal force. Because the tension and the force of friction are at a 90-degree angle, and because they are going left and right and not up and down, they have nothing to do with the normal force. Because of that, we just want to look at everything up and down. So we're actually going to say that this is the sum of the forces in the y direction. So let's just do this. The y direction is here. We're going to say up is positive. When I do this, I've also noticed that the block is moving left and right and not moving up and down. And because it's not moving up and down, we know that the acceleration in that direction is 0. Start with the sum of the forces is equal to ma. You could also say sum of the forces in the y is equal to 0. So you could have also just written this, sum of the forces in the y is equal to 0, because we know that acceleration is 0 because it's not moving in this direction or not accelerating in that direction. You'll get 1 point for doing that, so you have to do it. If you don't do it, you won't get that point. Then we need to say, well, what's positive? Fn is positive, that's up, minus m1g, which is down, and that's equal to 0. You will get a point for this. Then I would solve Fn is equal to m1g. You want to plug everything in. You do get a point for plugging everything in. You then get a point for the right number answer and the unit. If you don't put the unit and you don't put the number answer, you won't get that point. If you only put 60 newtons, you would get 1 point, but you would miss 1, 2, 3. So that is 1 out of 4 points. That's only a 25%. We want to do better than that, so you just have to be careful. For the next part, we want to find the force of friction. It's tempting to do a sum of the forces for this, but you don't want to. Instead, for the force of friction, we want to use the equation that's on the equation sheet. And you'll notice that equation is just the force of friction is equal to mu times Fn. Our mu value from the reading up top, you'll see, is 0.25. So the coefficient of kinetic friction is 0.25. So I have plugged that in right here. I already know the normal force is 60 newtons. So I plug that in here, multiply the two together, and I get 15 newtons. To score this one, it would be 1 point, 1 point, and then 1 point for the number and the unit. So make sure you have both. In the next part, they want us to derive an equation, then solve for the acceleration of block M1, starting with the sum of the forces, and then this says in the x direction. Remember, again, our x direction is not just left and right, it's also going down. So from left to right and from top to bottom over here, because this is a pulley. It's the only time you'll do that. I'm going to draw the free body diagram up here so that you can see what's going on. All right, here we go. Please notice that this is the same diagram, it's just without the boxes. And I've moved the M2G, just moved it up here so that I have a little bit more room. I want to find the sum of the forces. You could say in the x direction if you want to, since we said to the right is positive x and to the bottom here is positive x. That's equal to the total mass. Why do we have to do total mass? Well, we have two masses. And because they're connected by the string, they both accelerate at the same rate. So we're going to say that's equal to the total mass times the acceleration. Pointing in the positive direction, we have m2g. So we're going to start here with m2g. We're going to subtract ft, and that's this ft right here. We're going to add to that this ft, because remember, we're looking only in the x direction, and this is in the x direction. And we subtract the force of friction because it is in the negative x direction. That's equal to the total mass, so instead of mt, I've put m1 plus m2 times acceleration. Also notice this says derive an equation. You have to derive the equation and solve for the letter and then solve for the acceleration. So please make sure that you do that. If you stop here, you're going to miss a point, and I'll show you where the points come from here in a second. I'm going to cross off ft for both of these, and that gives me m2g minus ff equals m1 plus m2 times a. Now I'm going to divide both sides by m1 plus m2, and do that by both sides, 1 plus m2. And please notice the m2, you cannot cross it off. You have an addition sign here. You've got something separating the two. If you were multiplying the two, you still couldn't because you'd have the subtraction sign up here. But I did solve it for a. So the points for this would be 1 point for writing the sum of the forces equation. You have to do that. 1 point for having the two equations here. 1 point for then solving for a. At that point, now it's just plug and check. We're going to plug in our numbers, and then we're going to get our number answer with our units. And notice this should be a positive 2.1 meters per second squared. If we said down was negative and to the right was negative, then this would be negative 2.1 meters per second squared. So just be really careful with that. Let's go ahead and take a look at the next part. It says calculate the tension in the string connecting the two blocks. There's two ways to do this. We can either do it for the falling block. So remember, our free body diagram looks like this. This is M2G, and straight up is the force of tension. Or we can do it for the horizontal block, and remember for this one we've got our two things going up and down, so Fn, this one is M1G, and then pointing to the right and left, this would be the force of friction and the force of tension. So you can do it either way. You should get a number that's very, very, very close. This one's actually 27.65. So these two numbers differ by 0.05 newtons. And compared to 27 or 28 newtons, that's a very, very, very small error. So we don't worry about it. For the falling block, we're going to say the sum of the forces for object 2, which is the one that is hanging, is M2G, so that's positive, minus Ft equals M2A. We're going to solve for Ft. That means I subtract M2A from both sides and add Ft. That gives me this equation. We then have our numbers we plug in, and we end up with about 27.65 newtons. You could also do it horizontally. So we could say Ft minus Ff equals mass 1 times acceleration. Now where did that acceleration come from? Remember, it came from here. So on the test, if you make a mistake and you calculate the acceleration wrong, as long as you plug that number into this equation and everything here is fine, you'll get full points. Points from this, same thing for both. You get 1 point for writing the sum of the forces equation. So over on this side, it would be sum of the forces for number 1 is equal to M1A. So you would get 1 point for either of those. Then you would get 1 point for doing either of these, making sure that you show where all those come from. You get 1 point for showing the math, and then you get 1 point for having the correct answer. So that's another 4 points. You'll notice a lot of these are going to be 4 points. That's the end of number 1. Let's go ahead and take a look at number 2. So for number 2, we have a box. It's being pulled at a constant speed up an incline. Notice that this is an incline, which means we are going to absolutely positively need to make sure that we do components for this one. Okay? They tell that there's a pull here. We also see that there is a mu k, so there's our kinetic friction again, and we do know the angle is 30. The other thing they tell us is that the distance from here to here is 2 meters. We'll see if we even need that. On the left dot, you have to draw a free body diagram. That means no components. On the right dot, right here, we're going to draw everything with components. So I've done that for you already. Instead of using x and y for this one, we're going to use positive perpendicular and positive parallel for our two directions. Since FF, FN, and FP are in those two directions, we don't need to do components with those. We do need to do components with MG. Be really careful. You don't really want to draw your components like this because one of them is along the plane. We don't want it to be a component on our surface. That makes things super confusing. So instead of having it on the surface and looking at what we did there, what we're going to do is we're going to draw our component so that we have one line that is right here. So this line, you'll notice, is perpendicular to the surface, and the other one is parallel. When you get done, you should have lines that go in these directions. Notice this one comes straight down. We don't have one to the right like this. Instead, this one's coming down the hill like that. Why did I put positive parallel? Well, it's because I am pulling this up the ramp, and that's the direction of motion. So we want to try to keep these positives in the direction of motion. Next thing we need to do is find the normal force acting on the plane of the box. So to do that, one thing I want to show you is, remember, we always want our angle. If we think about a dot right here on our diagram, that's the same as this dot right here. And since this is 30 degrees, this is also 30 degrees, and that's through geometry. But if you just remember, as long as my dot is touching the plane and I have the same dot down on the bottom with the horizontal, those two angles are the same. This angle would not be 30. This angle is 60. So if you made the mistake of drawing this, you'd have to make sure that you see this angle is 60. Okay? So from here, this angle right here is 60. So that's this guy. We don't want to do that though. We want to be really careful that we stay away from anything that is touching the plane. That makes everything a lot more difficult. You can still do it, but it's not pretty. Let's take a look at the work that we did here. It says calculate the normal force. So here's the normal force. But I don't want to use this diagram because it doesn't show me everything. Here is the normal force that I want. And I need to look at everything that is in the positive and negative perpendicular direction. I'm going to circle that in yellow. It's going to be a little bit harder to see, but this is what is in that direction. mg cosine of the angle and Fn. Notice mg sine of the angle is going down the incline. So I'm going to erase that for just a second. I'm going to try to do this a little closer. And so this one, there's your two things that you need to worry about. At that point, what I did is I said sum of the forces perpendicular equal to 0. Then I went ahead and said, well, up is positive, up and to the left, so that's Fn minus mg cosine of the angle equals 0. That's a point. Plugging your numbers into the point and then getting the correct solution with the correct unit. Forget the unit, you won't get that point even though your number's right. That is your fourth point. If we look at this going left and right, okay, and by left and right I mean up and down the incline, it wants us to find the component of the force of gravity acting parallel to the plane. This is parallel to the plane, and it is a component of the force of gravity because this is the force of gravity and this is the component of that force of gravity. So that's looking mainly for your definitions. The equation you'll use here is Fg is equal to mg sine of the angle. You have to put that in. Then we're going to plug in our numbers. So that's 35 times 10 sine of 30, and we get 175 newtons. That was pretty easy to do. On the next page, they want us to find the force of friction between the plane and the box. Just like we did in the previous problem, we just used the force of friction equation. We did find earlier in letter B, we found the normal force. So this comes from letter B, and we just plug that in times 0.25. We get a final number then of 75.8, and our points come from here. 1 point for the equation, 1 for plugging in, and 1 for making sure that we have the number and the correct unit. For letter E, they want us to find the force applied by the person on the box. So let's just do a really quick sketch here of that situation. Now that I have my free body diagram with components, I can do this. There is no acceleration. Why is there no acceleration? Because we said that this is being pulled at a constant velocity. So because there's a constant velocity, that means that my acceleration is equal to 0. So that's really important to see. We're going to start with everything, and we only want to know in the parallel direction what's going on. So we've done the parallel right here. We have the force of the pull, that's what we want, minus the force of friction, but notice we also have mg sine of 30. So we have to subtract also mg sine of 30. You can't just subtract friction, you have to do everything that is pointing down to the left. And so that would be mg sine of 30 also. You'll get 1 point for the sum of the forces equation, 1 point for this equation. You then need to solve for FP and put the numbers in, and then you get your final answer. So hopefully that helps, and you really, really need to make sure that you know how to do these problems backwards, forwards, and inside out. I would download the packet that's on Canvas and sit down and do these until you can do them without looking at them. Don't rely on your partner because you don't know if they're going to know it or not. You want to be able to work together, and if neither of you know what to do, that's a huge problem. If you both know what to do, you can check each other. All right, that's it. Thanks.